Hello and welcome back. We now take our next step in getting to know how to work with PyTorch and deep learning and look at image classification. In this exercise, we'll build a simple model to analyze images and use the famous MNIST data that's originally used by Jan de Kan. The dataset contains about 70,000 images of handwritten digits between 0 and 9, 60,000 of which are typically used for training and then the rest for testing. So the reason we use this data set is because it's fairly simple and that allows us to run on CPUs instead of GPUs without waiting an extraordinary length of time. It will still be very slow on a CPU, but we still have a chance of doing this. More complex data will be hopeless on CPUs. Because this data is very simple, a few years ago the fashion company Zalando released a variant of this. It's called Fashion MNIST and it's to be used as a drop-in replacement. So it has very similar properties, the same number of images, the same number of classes, so 10 classes and so on. But instead of showing just handwritten digits, it shows different items of clothing like trousers, t-shirts and something like this. The main motivation for Zalando was because the MNIST data is really far too easy for any modern system, so it cannot really be used to develop algorithms. As I said, we stick here with the original data because we want to have a chance that we can actually do this and if we don't have access to the GPU. We will also use the PyTorch vision library that provides us with more convenience functions to access our data, and also if for your later use it comes with pre-trained models and commonly used image augmentation models. So we import the relevant libraries. In particular, we need Torch, the neural network library. We need access to the data loader, and this becomes a function that becomes important later on. We use the Torch vision library. It's commonly abbreviated with TV, and Plotlib and NumPy are our standard libraries that we need as well. As we said before, because this is a very standard practice data set, it's included in almost all libraries, and Torch Vision has also access to it, so we download it and transform it to a tensor directly. So if we do this and execute it, the code will retrieve the data from the web page, put it locally, and if already in our repository it's already there, but if it's missing, it will be downloaded. Now we need to prepare this. We define a batch size of 64 images, so these are the number of images that we use to calculate the gradients before we move on to the next one. We also need to create these data loaders. These are essentially convenience functions that we use later on to feed the data through the machine learning algorithm. We can, for example, print a simple example of it because the way the data loader works, we need to define a loop even if we want to only show one image. This is what we do here. We break out of this loop, but the data loader is really only to be used with loops, and so we need to do this and we can't just access it. Here we notice another thing. If we want to show the image, we need to transform it into the common Python format. Essentially, these images are just arrays of numbers, and if we want to visualize them, we need to convert them back so that Python, Matplotlib, understands how to visualize them. We use the grayscale for this. So now we have access to our data and we need to define our neural network. Before we can do this, we need to set it up ourselves. In particular, that means we need to define the architecture of the neural network, and we need to define the optimizer and other parameters that we need to train the network. So let's start by defining the neural network. In PyTorch, we do so by defining a class, and this inherits from NN. This is what we imported before from NN module, so the neural network module. And then we need to do two main steps. First of all, we need to implement the init method. So here we need to define the components that we want to use in our neural networks and anything else that we need to pass on. And then we need to implement the forward method. So this is the forward part of the neural network. And here we define how the model is built from the various components defined in the init method. The backward part of the training loop is implemented by PyTorch automatically. So what can we put in there? If we want to use a GPU, of course, then we need to move it over there. but we first need to think about how we build a model. So we have linear layers that we use, for example, for classifications, and then we have the non-linear layers, for example, ReLU as the activation function. We have regularization, dropout or dropout OD, and then we have convolutional neural network layers and max pool layers, and these are essentially used to handle images. So, for example, for text we would use something else, but here we focus on images, and the convolutional layers are essentially learnable image filters. So we have two hard constraints when we define our model. The input layer needs to be able to handle the data that comes from the data loaders. In our case, these are the images, and they are 28 by 28 pixel grayscale images. So the input layer needs to be able to handle this data size, and we need 10 nodes in the output layer because we have the digits from 0 to 9, right? So we have essentially a classification problem, and each class is one output node. Now let's first build a very simple network. And as an exercise, you can upgrade this to convolutional neural network layers. I will go over this in another video. So let's see how we can build this very simple neural network layer. We don't use convolutional neural networks for now. And note how we use the functional to pass the data through the various elements, for example, the activation function. So first of all, we need to move everything to the GPU if we have one. First of all, we identify if we have a GPU available, and then we use this variable later to move everything over to the GPU if we have one. Now we define our very simple model. As we said, we need to build our own class and inherit from NN module. That means we need to implement the special init function. And because we need to initialize our module, we pass this on with super to the base class. Right? So this is what we call up here. And then we have the components we want to use. For example, here we have a fully connected or linear layer. This is the input one. Notice here the 28 by 28. And here's the output one. Notice here the 10. And in between, we are essentially free to choose. So I've chosen our 512. And we have an intermediate layer to connect the input with the output layer. And now we need to define the forward pass. Right? First of all, we need to flatten the image. So that means that we pass sort of the two-dimensional image as a one-dimensional sequence of numbers. Notice here we have 28 times 28. So it's essentially a one-dimensional input, and flatten does that for us. Right? So x is the data, and you can see how it passes through. We always have x equals something x. So that means that it's always overwritten and passed on. So first we flatten this two-dimensional data into a one-dimensional list. Then we have the first fully connected layer. Then we use the activation function with the functional. Then we have the next layer, do the activation function again. We have the final layer, and now we return the data as they have run through the network. Now we create an instance of our new class, move it to the device like the GPU if we have one. We can also print the model and see what it does. Right? So this gives us a nice summary of where we are. Now we need to set up the further parameters of the network. So we need to do the optimizer and the loss function. And because we do a classification, the best thing to use is the cross-entropy loss. And we need to use the optimizer. We used, for example, just simple gradient descent previously. A much better one is the Adam optimizer with a learning rate. And we need to tell the optimizer which parameters they need to optimize. Remember, in the linear regression example, we did this manually. Here we asked the model which parameters it has. Now we move on to the network training. Essentially, the skeleton is the same. We loop over all the batches of the data, move the data to the device, either CPU or GPU, calculate the predictions with the current state of the neural network. This is the forward pass. Determine the quality of the prediction. This is our loss function. And then in the training loop, we need to tell PyTorch to do the backward propagation, update the network weights. So this is what the train loop does. We use the data loader for it. We have the model, the loss function, the optimizer, and we also keep track of the loss at the moment. So we need to put the model into training mode and then loop over all the batches in the data loader. So this is where the data loader comes in, and we access it, and it gives us a batch of data and the training and the labels. So we move the data to the device, make a prediction. This is here. We apply the current state of the model on the data, get a prediction, and calculate the loss function with the true labels and our prediction. Then we do the backward part. First of all, we erase all gradients, calculate the backward part. This is computing the gradients from the current state. And then tell the optimizer to move in the right direction, and then keep track of what's happening. We do a similar thing for the test data. Here we put the model explicitly into the evaluation mode, and we have the same data loader here, and we don't use gradients, so this becomes a bit simpler, but again, here we do the prediction of the current state of the model. Then we call this, and for now we just use 5 epochs. That should be enough. We record the loss values and the accuracies for our evaluation metrics, and just simply loop over the epochs and call the methods here. We have the training one, and remember that we want to record the loss function, so we pass on the training data, the model, the loss function, the optimizer, as we have defined before, and we compute the accuracy in the test module before, and when we're done, we print done. So here, as we go through, we can see how the model improves, and at the end, we plot the data that we have, that the loss function and the accuracy, and you can see that the loss function always goes down, the accuracy peaks and then drops down slightly. So here we would probably need to improve a bit if we were to use this. As you can see, with a very simple, fully connected network, we can already achieve a very good accuracy. That's not too bad. But if you look at the competitions, that for this very simple data set, you would have to beat essentially something very, very close to 100%, 99.8.